This lesson is about increasing and decreasing functions and involves the first derivative test. Okay, so we're going to know that a function is either increasing or decreasing based on its first derivative. Well, take a look here. When the first derivative is positive, then we know f is going to be increasing because it'll have a positive slope. When the first derivative is negative, we know it'll be decreasing. We'll have a decreasing function because the slope is negative. And when the first derivative is constant, then we know the slope is equal to 0. And we've looked at this before. So if we've got some sort of function, okay, so we might say it's increasing in this area here because the slope is going to be positive. It's also increasing in this area here, so we'll have a positive slope in that area. Okay, over here in this area, it looks like slope is negative, so it's decreasing. Also over here, decreasing in this area, and it's not very horizontal, but our first derivative is probably going to be 0 in this area because it's looking horizontal, and somewhat here too. Increasing going up, decreasing going down. Okay, now to find intervals where a function is increasing or decreasing, here's what we're going to do. First of all, we want to make sure that f is continuous on an open interval. First step, find our critical numbers in that interval. And that'll tell us our different test intervals that we're going to look at. Okay. So between our critical numbers, we're going to have our different intervals. And this will make more sense when we do these couple of examples. Then we got to determine the sign of f prime for some sort of value in each of those intervals. And we just pick whatever value you want, a test value. Make it an easy number to work with. Whatever looks easy. Again, this will make more sense when we look at what we're looking at. And this is we like to call this a sign chart. Sign charts are very handy in calculus, especially when looking at the first derivative test and the second derivative test. The only problem is you can't use a sign chart on your AP exam as justification points. So you can use a sign chart all you want on your exam, but readers aren't going to grade for that. Because merely having a sign chart doesn't necessarily show that you know exactly what you're talking about or what to do with that sign chart. That's where you have to make formal justifications with sentences, and we'll talk about that more as we go. But sign charts in and of themselves aren't bad. Just realize you have to do more than just show the sign chart. And then after you've got your sign chart, then just determine whether f is increasing or decreasing on that interval. What does that mean? Well, let's take a look. Here's some examples. Okay, let's take a look at this function here. We want to identify the open intervals on which this function here, h of x equals 12x minus x cubed, is either increasing or decreasing. So, first of all, we want to make sure this is continuous, and it's going to be, because it's a polynomial. So let's find the derivative first so we can find our critical numbers. So our h prime of x, find your derivative. Well, derivative of 12x is going to be 12. The derivative of x cubed, this will be minus 3x squared. And remember, your critical numbers are where your first derivative equals 0 or it doesn't exist. So we're going to set this equal to 0. 12 minus 3x squared equal to 0. And solving this, I'll have negative 12 equals negative 3x squared. X squared. I don't like this stylus. Equal to 4. So x has got to equal plus or minus 2. Don't forget the plus or minus because we're going to take the square root of that. So here's my critical numbers at positive 2 or negative 2. Okay, now there's not going to be anywhere where this derivative doesn't exist, because we don't have any values dividing by 0. No issues there. No issues with taking a root of a negative number, an even root of a negative number. Those are where we worry about our values that don't exist most. Okay, so we've got these two critical numbers. Well, those two critical numbers are going to break up our intervals. So our first critical number is negative 2. So as I'm looking at this sign chart, well, these are going to be, okay, so here's what our sign chart might look like. I've got my x values. Well, x is going to start from negative infinity until I get to my first critical number, which is a negative 2. There's one interval that I'm going to have to check on. And then when x equals negative 2, we know the derivative is 0. So then my next interval is going to start back on this open interval after negative 2 up until positive 2. And then at positive 2, my first derivative is 0. And my last interval is going to go from positive 2 out to positive infinity. Okay, so I've got two critical numbers. It breaks up my entire domain into three intervals here. Okay, so now I need to pick a test point in each of those intervals to plug into the derivative to tell whether that derivative is positive or negative, and then I can determine if it's increasing or decreasing. So, looking at h here. Okay, well, let's take a look. So let's pick a test value in this first interval. And we're going to check our derivative at that test value. Well, I just need a number in this interval from negative infinity to negative 2. Let's say, I don't know, how about negative 10? I can pick whatever I want, something in that interval. Well, it should look pretty obvious. If I plug in negative 10 into my derivative up here, I'm going to have 12 minus 3 times negative 10 squared. Well, that's going to be a positive number. It's going to be a negative 300. I'm going to get a negative value. I don't care what it is. I'm just looking for the sign. That's why it's called a sign chart. Okay, and then I'm going to do this for each of these. So, for this next interval, let's pick a number in between negative 2 and 2, like 0. Well, if I plug in 0, or any value in that interval, I'm going to get, well, 0 is going to be 12 minus 3 times 0 is 12. That's going to be positive. And if I check the last one, I can even pick the same value over here, like a positive 10. If I plug in 10 into my derivative, I'm going to have 12 minus 300 is going to be negative again. Okay, and then I go ahead and make my conclusion. Boy. Conclusion. C-O-N-C, illusion. Okay, so, since on this first interval, negative infinity to negative 2, the first derivative is negative, well, then that tells me this is decreasing in this interval. From negative 2 to positive 2, it's positive, so my function is increasing. Now the function is h, not the derivative, but the function. The derivative is positive, that means the function is increasing. For the last interval, the derivative is negative, that means the function is decreasing. So to wrap this up, to conclude, we would say h of x is increasing on this interval, negative 2 to 2, and decreasing on negative infinity to negative 2 and 2 to infinity. So that leads us to what we call the first derivative test. Okay, and I'll show you how this applies. For the first derivative test, it's not a test, this is just what they call it. C is a critical number, okay, of a continuous function in some interval a to b. Okay, so the first derivative test tells us if our derivative changes from negative to positive at that critical number, then we know that that point C, there's going to be a relative minimum at that x value of C. If the derivative changes from positive to negative at C, then there's going to be a relative maximum at that point. And if there's no sign change at C, at that value, at that critical point, then that critical number, then there's not a relative minimum or a relative maximum. And this should make sense. If the first derivative is changing from negative to positive, well, negative to positive, that means it's going from decreasing to increasing. Well, what's going to happen in between decreasing and increasing? There's going to be a relative minimum here. If the first derivative changes from positive, that means it's increasing, to negative, that means it's decreasing. There's going to be a relative maximum here. And if there's no sign change, well, maybe it's decreasing and then it's decreasing again. Okay? There might be a place where it's horizontal in between, decreasing and decreasing, or maybe it's increasing and then it goes horizontal for a minute and then increasing again. Okay, this is still a critical number here. It's just not a relative minimum or a relative maximum, because it's increasing and then it's increasing around that critical number. Pause here and make sure you get that all written down before we move on to an example. Okay, so they want us to apply the first derivative test to this function here. So, just like before, we're going to find our critical numbers and then determine what's going on around those to tell whether or not a certain value is a relative minimum or a relative maximum. Okay, so let's first find our derivative f prime of x cubed minus 6x squared. Well, derivative plus 15. Derivative of x cubed would be 3x squared minus derivative of 6x squared would be 12x, and 15 will be 0. So our critical numbers are where this equals 0. 3x squared minus 12x equals 0. This is a quadratic, so I'll need to factor. I can factor out a 3x, leaving me with x minus 4, which means I'm going to have critical numbers at 0 and 4. So, now I've got to figure out, so one of those or both of those are either going to be a relative minimum, a relative maximum, or neither. We've got to figure out what's going on around those based on those intervals. So our first interval, let's do a sign chart again. Our first interval is going to go from negative infinity to 0. We didn't say so, but there's not going to be any values here that give us where this first derivative doesn't exist. So we're good there. Our next interval is going to go from 0 to 4, and then our next one from 4 to infinity. Both of these only, this and the last example, only had 2 critical numbers, so we only have 3 intervals to check. If you have more critical numbers, you're going to have more to check, more test points to do. Okay, so let's check our sign of our derivative. Okay, this first interval, from negative infinity to 0, if I plug in any negative number I want, well, I'm going to have 3, think about this, This is 3 times a negative number squared. It doesn't even matter what it is. If I put in negative, say 1, that's going to be positive. Minus 12 times a negative 1, that's going to be positive. I'm going to get a positive result here. Okay. And then from 0 to 4, well, let's take a look. Let's say I have 1 again. Let's just do positive 1. 3 times 1 squared minus 12 times 1, that's going to be negative. And from 4 to infinity, let's do, how about 5? 3 times 5 squared minus 12 times 5. Well, that's going to be 5 squared is 25. 75 minus 60, that's going to be positive. So, in this first interval, since the first derivative is positive, the function is increasing here. Then it goes to decreasing. And then it goes back to increasing. So the first derivative test tells us, since here at x equals 0, my function goes from increasing to decreasing, from positive to negative, there's going to be a relative maximum at x equals 0, right here. And then right here, since the function goes from decreasing to increasing, or from negative to positive, there's going to be a relative minimum at x equals 4. And that's how we apply our first derivative test. Find your critical points. If the derivative changes from positive to negative, or negative to positive at those critical points, then we know we have a relative minimum or relative maximum. Okay, so here's your assignment. Page 183, 3 to 35 odd, 41 to 43 odd, and 57 through 62.